Hello students, in this video we'll see how special limits of functions of two variables can be converted to polar coordinates. Let's suppose that our function f of xy has the special form. It's a function g of the square root of x squared plus y squared. So let's suppose our function f of xy is of this particular form. Now this x squared plus y squared, x squared plus y squared square rooted is exactly just r, the polar variable in polar coordinates. So if we're computing the limit as xy goes to 0, 0 of f of xy, if we're computing this limit over here, let's think about this for a second. So xy converges to 0, 0 if and only if what? If and only if the square root of x squared plus y squared is going to 0. But that is nothing more than just saying that r goes to 0 if and only if r approaches 0. So xy, the point xy, converges to the origin point if and only if this radial variable goes to 0. So with this in mind, we can write this as just the limit as r goes to 0 of g of r. So what we've done here is we've turned our two-dimensional limit problem into a one-dimensional limit. So we've turned into a one-dimensional limit problem, which is good news. So let's see an example of how we would do this in practice. So here's one example. Let's find the limit as xy goes to 0, 0 of 1 minus the cosine of the square root of x squared plus y squared. I'm trying to make it very, very transparent here, over x squared plus y squared, okay? So let's do it. So we can notice over here that we can rewrite this limit in polar coordinates because this term x squared plus y squared square rooted is just straight up r, and this term in the denominator is r squared. So this limit is identically equal to, so solution, our limit in polar coordinates is, it's nothing more than just the limit as r goes to 0 of 1 minus the cosine of r over r squared. And now we pause for a minute and we think that, okay, if I plug in r equals 0, I'm going to get a 1 minus the cosine of 0. That's 1 minus 1 or 0 over 0. So I'm going to need to apply L'Hopital's rule. So we can use L'Hopital's rule or any other sort of limit trick you'd like to use. By L'Hopital's rule, this is the same thing as the limit as r goes to 0 of the derivative at the top is just going to be the sine of r, because the negatives will cancel, and then over 2r. And now again, this is a very common limit, but let's do L'Hopital's rule again. If I have the limit as r goes to 0 sine r over 2r, I have a 0 over 0. So if we use one more L'Hopital application, so by L'Hopital one more time, we're going to have the limit as r goes to 0 of the cosine of r over 2, and now we see that this is 1/2. So by translating this problem into polar coordinates, we got a relatively short limit problem, even though we have to use L'Hopital's rule twice. So we can conclude from this statement that this limit is equal to 1/2. So whenever we see the expression x squared plus y squared in the limit problem, see if we can write everything in terms of the radial variable. Then you can transfer the problem and make the problem a one-dimensional limit problem, which is actually much easier. Thank you very much.